Electricity and Electronics, Chapter 9. This is Section 3, Motors, Generators, and Power Distribution, which includes the chapters on your screen. Chapter 9, Magnetism. The objectives in this chapter is to explain the basic magnetic principles, state the 3 laws of magnetism, describe the link between the electric current and magnetism, explain Roland's law, discuss various types of relays and the manner in which they work, describe the use of magnetic shields. Some of the keywords used are the ampere turns, or AT or NI, electromagnet, field intensity, flux density, Gauss, Hilbert, left-hand rule for coils, left-hand rule for conductors, lodestone, magnet, magnetic flux, magnetic shielding, normally closed or NC, normally open or NO, permeability, relay, reluctance, residual magnetism, Roland's law, and solenoid. Basic magnetic principles. For centuries, magnetism has been of interest to people of all sorts. Shepherds tending their flocks in ancient days were mystified by small pieces of stone that were attracted to the iron tip of the shepherd's staff. The ancient Chinese navigators discovered a small piece of this odd stone attached to a string would always turn in a northerly direction. These small stones were iron ore. They were called magnetite by the Greeks because they were found near Magnesia in Asia Minor. Since mariners used those stones in the navigation of their ships, the stones became known as leading stones or lodestones. These were the first forms of natural magnets. Today, a magnet can be defined as a material or substance that has the power to attract iron, steel, or other magnetic materials. Through laboratory experiments, it was discovered that the greatest attractive force appeared at the end of a magnet. These concentrations of magnetic force are called magnetic poles. Each magnet has a north pole and a south pole. It was also discovered that many invisible lines of magnetic force existed between the poles. Each line of force was an independent line. None of the lines cross or touch a bordering line. In figure 9-1 shows the magnetic lines of force. This field picture was created by placing a bar magnet beneath a sheet of paper and sprinkling it with fine iron filings. Notice the patterns of lines existing between the poles. These lines or of filings reflect the lines of force. Note the concentration of lines at each end of the magnet or its poles. The lines of force are more concentrated at the poles. Each magnetic line of force travels from the North Pole to the South Pole through space. The line returns to the North Pole through the magnet itself. These closed loops of the magnetic field can be described as magnetic circuits. Compare the magnetic circuit to the electrical circuit. The magnetizing force can be compared to voltage, and the magnetic lines of force can be compared to current. Further scientific investigation showed that the Earth acts as one enormous magnet. The Earth's magnetic poles are close to the north and south geographic poles. Refer to figure 9-2. You can observe that magnetic north and north geographic pole do not coincide. A compass would not necessarily point toward true north. This angle between the true north and the magnetic north is called the angle of declination or the angle of variation. There is, however, a line around the Earth where the angle of declination is 0. When standing on this line, your compass would point to true north as well as magnetic north. At all other locations on the surface of the Earth, the compass reading must be corrected to find true north. Laws of magnetism. The power of a magnet to attract irons has already been discussed. In figure 9-3, two bar magnets have been hung in wire saddles and free to turn. Notice that when the north pole of one magnet is close to the south pole of the other, an attractive force brings the two magnets together. If the magnets are turned so that the two north poles or two south poles are close to each other, there is a repulsive force between the two magnets. This demonstrates two of the laws of magnetism. These laws are stated: like poles repel each other and unlike poles attract each other. Place the two magnets under a sheet of paper. Using the iron filings to detect the invisible field, observe that the field is very strong between the two poles. Figure 9-4 top, however, when the magnets are placed with like together, the repulsive force is shown by an absence of lines between the poles. Figure 9-4 at the bottom. Caution: certain precautions should be observed during the handling of and storage of permanent magnets. Magnetism is a result of molecular alignment. Any rough handling, such as the dropping or pounding of the magnets, can upset the molecular alignment and weaken the magnet. What causes a substance to become magnetized? The molecules in an iron bar act as tiny magnets. If these tiny magnets are in a random order, such as in figure 9-5 on top, the bar does not act as a magnet. However, when these tiny magnets are arranged so that their north and south poles are in line, figure 9-5 bottom, the iron is magnetized. This can be demonstrated by breaking a piece of magnetized iron into several pieces. Each of the broken pieces acts as a separate magnet. Figure 9-6 shows a broken magnet when the iron is demagnetized. These molecules are placed back in a random position. The molecular action is further demonstrated by the way a magnet is made. For example, take an unmagnetized iron bar, rub it a few times in the same direction with a permanent magnet, and test. Bring the bar near some iron filings, and it will show that the bar is now magnetized. Rubbing the iron bar with the magnet lines up the molecules. Rubbing the iron bar with the magnet lines up the molecules and causes the iron to become magnetized. Permanent magnets are made by placing the material to be magnetized in a very strong magnetic field. Bar magnets should be stored in pairs with north and south poles together to ensure their long life. A single horseshoe magnet may be preserved by placing a small piece of soft iron called a taper across its poles. Permanent magnets are made in a number of shapes and sizes, such as figure 9-7. Flexible magnets may be used as a visual teaching aid. They are held in place on sheet iron by magnetism. Industry uses these boards for traffic control, production, flow, temporary notices, and other announcements. You will find similar but smaller flexible magnets on refrigerators in almost any home. Figure 9-8. These magnets are created by mixing steel filings with the rubber. These flexible rubber-steel combinations are placed in a magnetic field. Caution: heat will destroy a magnet. Heat energy causes an increase in molecular activity and expansion. This permits the molecules to return to their random positions on the unmagnetized piece of iron. Recording tape, used in cassettes, videotapes, and computers, stores information through the use of magnetic principles. Magnetized iron oxide particles are adhered to a plastic tape or data disc using a binder. By magnetizing these particles with a recording head, audio or video information, photographs, or data can be stored. Likewise, the information can be read from a tape or data disc. Magnetic flux. The invisible lines of magnetic force surrounding a magnet are called magnetic flux. If a magnet is strong, these lines of flux will become dense, so the strength of a magnetic field can be determined by the field's flux density, or the number of lines per square inch, or per square centimeter. Flux density is expressed by the equation B equals flux density divided by B equals pi divided by A, where B equals flux density, the symbol, the Greek letter phi, pi, equals the number of lines, and A equals the cross-sectional area. The cross-sectional area can be measured in square inches or square centimeters. If the cross-sectional area is measured in square centimeters, then the number of lines per square centimeter. If the cross-sectional area is measured in square centimeters, then the flux density is given in the unit Gauss. A Gauss is the number of lines per square centimeter. The flux B is usually given in Webers per square meter. Electric current and magnetism. During the 18th and 19th centuries, a great deal of research was directed toward discovering the link between electricity and magnetism. A Danish physicist, Hans Christian Ørsted, discovered that a magnetic field existed around a conductor carrying an electric current. You can perform an experiment that shows the magnetic field around the current-carrying conductor. Pass a current-carrying conductor through a sheet of cardboard. Place small compasses close to the conductor. The compasses will point in the direction of the magnetic lines of force, figure 9-9. Reversing the current will also reverse the direction of the compasses by 180 degrees. This shows that the direction of the magnetic field depends upon the direction of the current. The left-hand rule for conductors can be used to determine the direction of the magnetic field around the current-carrying conductor. Grasp the conductor with your left hand, extending your thumb in the direction of the current. Your finger curling around the conductor indicates the circular direction of magnetic field, figure 9-10. Figure 9-11, picture the dot in the center of the conductor on the left hand as the point of an arrow. This shows that current is flowing toward you. The circular arrows show the direction of the magnetic field. This principle is very important when electrical wires carry alternating currents. This is because the placement of wires or lead dress has an influence in the workings of a circuit. Conductors are grouped in pairs whenever possible to eliminate heating effects and radio interference caused by the magnetic field created by the current flow. The National Electric Code requires that wires be run in pairs to help eliminate this heating effect. Magnetic circuits. A detailed study of magnetic circuits is beyond the scope of this text. However, you should know the terms used to describe the quantities and characteristics of magnetic circuits. Reluctance. It has already been mentioned that a likeness exists between magnetic circuits and electrical circuits. In addition, a law of magnetic circuits exists
that is comparable to Ohm's law for electrical circuits. This law is known as Roland's law. Roland's law states that the number of lines of magnetic flux comparable to the current in electrical circuits is in direct proportion to the force comparable to voltage in the electrical circuits producing them. This force, capital F, is in units of magnetomotive force called Gilberts. Also, there is resistance to the magnetic flux in a magnetic circuit. The resistance to magnetic flux is called reluctance. Reluctance is measured in Gilberts per Maxwell or in amperes turns per Weber. 1 ampere turn per Weber is sometimes called a rel. The equation shown on your screen is where the phi total equals the total number of magnetic force, the F equals the force producing the field, and the R resistance to the magnetic flux, which is reluctance. The relationship between F and Gilberts and ampere turns is a factor of 1.257. This relationship is stated in the formula shown on the screen, where F is the force in Gilberts, I is the current, and N is the number of turns. The term reluctance has been defined as the unit of measurement of the resistance to the passage of magnetic lines of force. Experimentation proves that as the flux path increases in length, their reluctance increases. Likewise, as the cross-sectional area of the flux path decreases, the reluctance increases. Permeability and field intensity. Reluctance also depends upon the material used as the path. The ability of a material or a substance to conduct magnetic lines of force is called permeability. The permeability of air is considered to be 1. Materials with permeability higher than 1 conduct lines of force better than air. Materials with permeability lower than 1 offer more resistance than magnetic lines of force. Offer more resistance to magnetic lines of force. Permeability is expressed in the Greek by the Greek letter micro, or pronounced mu. The factors determining the resistance in a magnetic circuit can be compared to the factors affecting the resistance of electron flow in a conductor. For this, review chapter 4. So for the magnetic circuit, where R equals reluctance, this is shown on your screen, L is the length of path, and mu is the permeability of the material in the path, and A is the cross-sectional area of the path. There is a distinct link between the density of a magnetic field, the force producing the field, and the permeability of the substance in which the field is produced. So mathematically, as shown in your screen, the symbol H is the field intensity of a magnetizing force through a unit of length. It is commonly expressed in Gilberts per centimeter. In this case, mathematically, L is again the length of path expressed in centimeters. When making calculations, B, H, and mu of common magnetic materials can be found in an electricity handbook. The solenoid. When a current-carrying conductor is wound onto a coil or a solenoid, the magnetic fields circling the conductor seem to merge or join together. A solenoid will appear as a magnetic field with a N pole at one end and an S pole at the opposite end. This solenoid is shown in figure 9-12. The left-hand rule for coils can be used to determine the polarity of the coil. Grasp the coil with your left hand in such manner that your fingers circle the coil in the direction of current flow. Your extended thumb will point to the N pole of the coil, figure 9-13. The strength of the magnetic field of a solenoid depends upon the number of turns of wire in the coil and the size of the current in amperes flowing through the coil. The product of the amperes and turns is called the ampere turns, or AT, or NI, of a coil. This is the unit of measurement of field strength. If, for example, a coil of 500 amperes turns will produce a field strength required for some situation, any combination of turns and amperes totaling 500 will work. See the examples shown on your screen. Electromagnets. In the solenoid just discussed, air is the only conductor of the magnetic field. Other substances conduct magnetic lines of force better than air. These materials would be described as having greater permeability. To demonstrate this, a soft iron core can be inserted in the solenoid coil, figure 9-14. The strength of the magnetic field is greatly increased. There are two reasons for this increase. First, the magnetic lines have been concentrated into the smaller cross-sectional area of the core. Secondly, the iron provides a far better path, greater permeability, for the magnetic lines. This device, solenoid with an iron core, is known as an electromagnet. The rules used to learn the polarity of an electromagnet are the same as those for the solenoid. Use the same left-hand rule. When an electromagnet is energized, it is a powerful magnet. When the electrical energy is disconnected, the electromagnet loses most of its magnetism, but not all. If the depowered magnet is brought near some iron filings, the filings will be attracted to the core because the iron core has retained a small amount of its magnetism. This magnetism is called residual magnetism. If very little magnetism remains, the core would be considered as having low retentivity. Retentivity, then, is the ability of a material to retain magnetism after the magnetizing field has been removed. If a core retains a good deal of magnetism, it is said to have high retentivity. A soft iron core shows low retentivity. A steel core has high retentivity. Review questions for section 9.2. What is an electromagnet? It is a solenoid with a soft iron core. Question 2. Explain the left-hand rule for coils. Again, the left-hand rule for coils can be used to determine the polarity of the coil. Grasp the coil with your left hand in such manner that your fingers circle the coil in the direction of the current flow. Your extended thumb will point to the end pole of the coil. Question 4. What is permeability? It is the ability for a material to carry magnetic flux lines. Question 5. The amount of magnetism left in a magnetic core is called residual magnetism. Question 6. The unit of measure for magnetomotive force is, pick a choice, A, flux, B, Gilbert, C, Gauss, or D, none of the above. The right question is B, Gilbert, also written as capital F. The relay. The relay is a device used to control a large flow of current by means of a low voltage, low current circuit. A relay is a magnetic switch. When a relay's coil is magnetized, its attractive force pulls the lever arm, called a armature, toward the coil. The contact points on the armature will open or close depending on the normally at rest position. The phrase normally at rest position refers to the position of the contact before the solenoid is energized. If the normally at rest position of the contact is touching, the large current will flow until the relay is activated. Activating the relay opens the circuit. If the normally at rest position of the contacts is open, then activating the relay will close the circuit. Current will then flow until the relay turns off. Examine the schematic in figure 9-15. In this circuit, a light bulb is connected to a 115 volt power source. This setup is an example of controlling a 115 volt AC circuit with a 1.5 volt DC power source. The two different voltages are set to be mechanically connected by the relay. They are not considered electrically connected. The advantages of this device are clear. From a safety point of view, the operator touches only a harmless low voltage circuit, yet controls perhaps several hundred volts by the means of the relay. The heavy current machines can be controlled from a remote location without any need to run heavy wires to the controlling switch. The switch in action by means of relays can be very rapid. Some common relay applications include large lighting loads, heavy current in automobiles, such as headlights, and the control of electric motors. Relays are commonly found around the home as part of the air conditioning and heating systems. They are used to control the starting and stopping of electrical motors used in manufacturing systems. Relay logic is used in industry to control the proper sequence and control of electrical automation systems. Relays are also a vital part of electrical appliances, office machines such as copiers, and high voltage switching systems used by the power company. There are thousands of electrical applications involving relays. However, relay logic is rapidly being replaced by solid-state electronic systems and computers. Looking through a parts catalog, you will notice various relay designs. Figure 9-16, for example. When choosing a relay for a special purpose, there are several things to be considered. Three important considerations are the number of contacts, the amount of current the relay must carry, and its de-energized position. Well-designed relays have points made of silver alloys, tungsten, or other alloys. A relay can be chosen to open or to close a circuit. A relay can even be both normally closed in the de-energized position, and normally open in the de-energized position, contacts. The term normally open and normally closed are usually abbreviated NO and NC. The number of contacts and their de-energized position should be specified. The coil is the most vital specification. The coil chosen needs to produce a large enough magnetic field at its rated voltage to ensure positive contact of switch points at all times. However, most relays are so sensitive they require only a milliampere or less to energize, so care must be taken. In addition, relays are designed with coils that work on direct current or alternating current. You cannot energize a DC coil with an AC voltage or an AC designed coil with a DC voltage. Doing this may result in an electrical fire. A detailed explanation of these principles is found in Chapter 14, dealing with inductive reactance. Time relays. Certain relays are designed to have an adjustable time delay incorporated into the coil action of the relay. The time delay can be either a time delay or a time delay off. A time delay on means that after the relay is energized, there is a pause before the contacts close. The relay can also be designed as a time delay off. Time delay off means that after the coil is energized. Time delay off means that after the coil is de-energized, there is a time delay before the relay contacts change their position. Today, many time delay relays are designed to function as both time delay on or off. The reed relay. The reed relay is another use of magnetism, much like the ones we have already discussed. Refer to figure 9-17. Two magnetically sensitive switch contacts are enclosed in a glass tube. If a permanent magnet is brought close to the glass tube, it causes the switch contact to close. The relay can also be operated by an electromagnet. The operating coil is placed around the reed relay. Magnetic circuit breaker. When referring to electromagnets, the strength of a magnetic field depends upon the ampere turns. If a coil is made with a fixed number of turns, then its field strength may be varied by controlling the current in the coil. The magnetic trip breaker is devised upon this principle. The magnetic trip breaker is usually referred to as an instantaneous breaker because there is very little time delay in its tripping action during an overload condition. The instantaneous breaker will trip approximately 1/120th or 1/20th of a second if the current exceeds the rating of the breaker. The magnetic circuit breakers are usually adjustable. This means that a current range of 10 to 20% of the breaker is rated current. This means that a current range from 10 to 20% of the breaker rated current can be set. Look at the electromechanical coil and armature parts in figure 9-18. Compare this device to the relay. Notice that in the circuit breaker, the coil and the armature points are in series, and the entire device is connected in series in the line carrying the load. If the line current exceeds a preset value, the coil will build up enough magnetic force to overcome the spring tension of the armature. The armature releases the points and will open the circuits. The contact points must be reset or closed by hand. This device prevents a circuit from being overloaded beyond the safe capacity of the wires. An electrical code usually requires this type of device when there is a higher than normal danger of fire because caused by overload. The use of circuit breakers in a petroleum refinery is an example of their importance. In a location such as a refinery, an electrical fire could result in a dangerous explosion. Lesson in safety. The circuit breaker is installed for safety. It prevents overloaded circuits and the danger of fire. The breaker should never be disabled or bypassed. If the breaker opens a circuit repeatedly, locate the condition that is causing the excessive current and take immediate corrective action. The buzzer and doorbell. A common device that uses electromagnets is the buzzer. Arrange the coils and armature as in figure 9-19. Notice that the coil and the contact point are again connected in series. When the coil is energized, the armature is attracted toward the coil. The contact points open and break the circuit. The attraction of the coil then falls to zero. The armature springs pull the contact points closed. This once again energizes the coil and opens the contacts. This action continues as long as a voltage is applied. The device buzzes due to vibration of the armature. An extension may be placed on the vibrating armature to which a striker is attached. This striker hits a bell. This is the principle of the doorbell. More examples of electromagnetic uses are discussed later in this text. A thorough understanding of the action of magnetic field is vital. The principles of magnetism are the basis of many electrical and electronic applications, such as radio, television, motors, generators, transformers, speakers, and many others. Learn the basic principles well, and other applications will be very easy to grasp. Magnetic shields. A magnetic field has no bounds. For the first time a student, it is hard to understand that the force of the magnet will pass through any type of substance. It does not matter whether the substance is a concrete wall, a glass, or wood. However, an instrument or a circuit can be shielded from magnetic lines of force. This shielding is done by using the permeability of some other substance. The magnetic lines of force will flow through the path of least resistance. If a piece of iron is placed in a magnetic field, the lines of force will follow through the iron rather than through the air. This is because the iron has much greater permeability. The iron acts as a low resistance path for magnetic lines. So in figure 9-20, this action can be observed. By this method, magnetic lines may be conducted around the object that needs to be shielded. This is called magnetic shielding. Many shields are used in electronic equipment to prevent magnetic fields from interfering with the working circuits. Magnetic levitation, transportation. One of the fastest growing areas of magnetic application is the use of magnetism to elevate a train car and then propel it on the rails using magnetism. The rails are made up of long series of solenoids. The rails are made of a long series of solenoids mounted along a track. When the solenoids are energized, the train is elevated above the track. This construction eliminates the need for wheels, axles, or electric motors, which are the main causes of speed reducing friction within the system. Once elevated above the track, the solenoids receive a signal or signals that are sequenced by a computer. The computer energizes the solenoids one by one in such a way that the car can gradually increase its speed to over 200 miles per hour as it is propelled along the rail. This propulsion is based on the magnetic attraction and repulsion principles learned in this chapter. Now for the review questions for section 9.3. What is a relay? It is a magnetic switch or device made up of a solenoid, an iron core, and an armature or lever arm. Question 2. The strength of a magnetic field in an electromagnet depends on its ampere turns, or AT, also called Ni. Question 3. A circuit breaker is A. It is installed for safety. B. Opens overloaded circuits. C. It is often used in place of a fuse. And D. Is all of the above. D. All of the above is the correct answer. Question 4. Explain how a door buzzer operates. In a door buzzer, when the coil is energized, the armature is attracted toward the coil. The contact points open and break the circuit. The attraction to the coil then falls to zero. The armature spring pulls the contact points closed. This once again energizes the coil and opens the contacts. This action continues on and on as long as the voltage is applied. The device buzzes due to the vibration of the armature. An extension may be placed on the vibrating armature to which the striker is attached. The striker hits a bell. This is the principle of a doorbell. Question 5. What is magnetic shielding? Magnetic shielding provides with a permeable material to deflect magnetic flux lines. Summary. Magnets are materials or substances that have the power to attract iron steel, and other magnetic material. Magnets have poles. Every magnet has a north and a south pole. The Earth is a large magnet. Like poles repel each other and unlike poles attract each other. Temporary magnets lose their properties quickly. Permanent magnets keep their magnetic properties for a long period of time. The invisible lines around a magnet are called magnetic flux lines. Electromagnets are created when current flows through a coil of wire. Magnetic resistance is reluctance. Permeability is the ability of a material to conduct magnetic lines of force. Residual magnetism is left in a core after an electromagnetic field is turned off. The relay is an electromagnet or electromagnetic switch. An electromagnetic circuit breaker can be used to prevent an overload current or an overload of current. Lastly, magnetic shielding uses materials with high permeabilities to draw magnetic flux away from sensitive devices. As you knowledge questions for this chapter, concentrations of magnetic force are called field intensity. What is the name of the angle between true north and magnetic north? That is the declination angle. State the first two laws of magnetism. Like poles repel, and unlike poles attract. What is the equation for flux density? And what do each of the letter symbols in the equation stand for? The equation for flux density, as seen in your text, chapter 9, page 128, is B equals to phi divided A, where B is equals to flux density, pi or phi equals the number of lines, and A equals the cross-sectional area. Question 5, state the third law of magnetism. That is, the attractive force increases as the distance decreases. Question 6, compare a magnetic circuit to an electrical circuit. Use Roland's law. Using Roland's law states that the number of lines of magnetic flux, which are comparable to the current in electrical circuits, is in direct proportion to the force comparable to the voltage in electrical circuits producing them. This force is in units of magnetomotive force, called Gilberts. Also, there is resistance to the magnetic flux in a magnetic circuit. This resistance to magnetic flux is called reluctance. Reluctance is measured in Gilberts per Maxwell or in amperes turns per Weber. So 1 ampere turn per Weber is sometimes called a rel. Question 7, list 3 advantages of using relays. From a safety standpoint, the operator touches only a harmless low voltage circuit, yet controls perhaps several hundred volts by means of the relay. The heavy current machines can be controlled from a remote location without any need to turn or to run heavy wires to the controlling switch. And finally, switching action by means of relays can be very rapid. In your own words, State the meaning of the following letters, symbols. And just as a individual example, I have H, field intensity or magnetic field strength. The mu is the permeability or ease of conductance of flux lines. And the Ni is the number of turns per ampere-turns ratio. That determines the strength of a magnetic field. And that wraps up chapter 10. Now I'll move on to experiments. I'll describe the experiments so you can go ahead and perform those. Experiment 9-1, observing magnetic lines of force. In this experiment, you'll observe the placement of the lines of force emanating from permanent magnets. For this, you will need 2 bar-shaped permanent magnets, 1 piece of cardboard, and a small quantity of iron filings. Step 1 is to place the magnets on a table facing so that the poles attract. Keep the magnets' ends from touching. You may need to place a non-magnetic object between the magnets to keep them separated. Step 2 is to place the cardboard on top of the magnets. Sprinkle iron filings on the cardboard and observe the pattern. Copy the pattern onto a sheet of paper. Remove the cardboard and the filings. Step 3, place the magnets on the table so that the poles repel. Step 4, place the cardboard on the magnets and sprinkle the filings on the cardboard again. Observe the pattern. Copy the pattern and then remove the cardboard and the filings. Step 5 is to place the magnets on the table so that 2 attracting ends touch. Step 6 is to place the cardboard on the magnets and sprinkle the filings. And then observe and copy the pattern. In the end, what conclusions can you draw from these observations? Experiment 9-2, testing an electromagnet. Use an electromagnet to examine the effect of current direction on a magnetic field. Note that you may use a pre-wound solenoid or build one yourself. Instructions for building a solenoid and other parts for an electromagnet experiment can be found in Appendix 6. The materials include 1 battery or 9-volt battery, 1 pre-wound solenoid coil with iron core, or see Appendix 6 to build one, 1 compass, and pieces of insulated connection wire. And step 1 is to set up the circuit shown in the schematic in Exhibit 9-2A. The electromagnet is connected to a 9-volt battery. In Exhibit 9-2B, step 2, bring the tip of the iron core of the electromagnet near the compass. What do you observe? See Exhibit 9-2B, notice the polarity of the coil. In Exhibit 9-2B, compare your results. Step 3 is to reverse the connections of the battery. Observe the compass action. Remember the direction of the electron flow in a circuit. Does this experiment prove the left-hand rule? That is Experiment 9-2. I highly suggest you perform that. Experiment 9-3, Residual Magnetism. Using the electromagnet from Experiment 9-2, examine magnetism and residual magnetism. Materials include again 1 9-volt battery, 1 pre-wound solenoid coil with iron core, 1 switch, small steel nails, iron filings, pieces of insulated connection wire. Step 1 is to set up the circuit shown in the schematic in 9-3A. This schematic has an electromagnet connected in series with the 9-volt battery and the switch. Step 2 is to close the switch and bring the tip of the iron core of the electromagnet near the small nails. What do you observe? See Exhibit 9-3B. Step 3, as the nails are held by magnetic force, open the switch. Do the nails stay attached or fall? Step 4, leaving the switch open, bring the tip of the iron core near the iron filings. What do you observe? Experiment 9-4, testing a solenoid. Experiment 9-4, testing a solenoid. In this experiment, you will demonstrate the magnetic attraction developed by a solenoid. The materials needed are one 9-volt battery, a pre-wound solenoid coil with iron or steel core. Core needs small hole drilled through one end. You need one switch, you need one metal plate with stand, and you need one small rubber band, pieces of insulated connection wire. Step 1 is to set up the circuit shown in the schematic Exhibit 9-4A. Leave the core out of the electromagnet. Step 2 is to energize the solenoid coil by closing the switch. Step 3 is to bring the iron core close to one end of the coil. You should feel the pulling magnetic force. Step 4 is to release the core from your fingers. The core will be drawn into and come to rest at the center of the coil. Step 5 referred to Exhibit 9-4B. It shows a simpler door, or a simple door, chime. This is built by arranging the coil and parts as shown. Step 6, set up the store chime circuit, Exhibit 9-4C, which shows a completed setup. Step 7, energize the coil. What happens to the core? Step 8, open the switch. Did your chime work? These experiments show converting magnetism into mechanical motion. Solenoid magnetic attraction principles has many uses in industry. How many can you come up with? And a quick discussion about the electric guitar. Some may be interested, some not so much, but yet it could show some of the principles just learned about magnetism. The electric guitar uses a transducer called a pickup. There are several variations of pickups on the market, but they all have similar operating principles. The pickup on a guitar is usually constructed of a winding and a magnet or a piezo cell crystal. The steel strings of the guitar vibrate across the pickup. This causes a slight voltage to be produced in the pickup coil. The AC wave of the voltage in the pickup coil is a frequency equal to a pitch of musical sound. If properly tuned, a guitar string that vibrates 440 times a second will produce a 440 Hz electrical frequency. When a 440 Hz electrical frequency is amplified and wired to a speaker, a perfectly pitched musical tone is produced from the speaker. Musicians run their fingers up and down the frets board of their guitars. This causes the length of the string to vary. This action varies the pitch or frequency of the tone or of the note. Some frequencies sound great and are in perfect pitch. Other frequencies sound flat and out of tune. In these cases, the musician may blame the guitar. However, a tuned electric guitar will recreate an exact vibration produced by the musician. Congratulations, you have completed this lesson. After you've finished all the reviews, quizzes, tests, and experiments, you will have earned this electronic course rank. This has been Chapter 9. Thank you very much for listening, and Good luck in the rest of your studies.